Welcome to topic 13.1, hydrocarbons. Here we will see some key concepts in organic chemistry and introduce the first families of organic compounds that you need to know for the Leaving Cert. Organic chemistry is the chemistry of carbon, and as such it's the chemistry of 4 valence electrons, and so it's the chemistry of 4 covalent bonds. Carbon atoms can arrange their bonds in multiple configurations. A carbon atom can have 4 single bonds around it and be bonded to 4 other atoms. When it has 4 single bonds in this way, it will always have a tetrahedral arrangement with a bond angle of 109.5 degrees. In this situation, we would refer to the carbon as being a tetrahedral carbon. Methane, CH4, is the simplest example of this structure. Instead of 4 single bonds, a carbon atom could instead have its 4 bonds in the form of 2 double bonds, as in the case of carbon dioxide, CO2. Here you can see that the bond angle is 180 degrees, and it has a linear arrangement. A carbon atom could also configure its 4 bonds as 1 double bond and 2 single bonds, as in the case of methanol, HCHO. Here the carbon is double bonded to an oxygen atom and has single bonds with 2 hydrogen atoms. We would describe the carbon in this molecule as being a planar carbon, because all of the atoms around it can be arranged in the same plane as shown. Lastly, carbon could arrange its 4 bonds in the form of 1 triple bond and 1 single bond, as we see here in the case of hydrogen cyanide. Again, we would describe the carbon here as being a planar carbon since all of the other atoms can be arranged in the same plane. Here the bond angle is 180 degrees. As well as being able to bond with a wide variety of elements, carbon can also bond with itself, of course, and can form rings and long chains of carbon atoms. Such a chain of carbon atoms is often referred to as the backbone of the molecule, as it forms the core of many organic compounds. All in all, this makes carbon chemically very versatile, and it can form a huge range of different compounds. Indeed, the vast majority of known compounds are organic. Without this incredible variety, life would never have been possible, and this is why we often refer to life as being carbon-based. In this video, we will look at 3 families of compounds: the alkanes, the alkenes, and the alkynes. These families are usually considered together as they are all classified as hydrocarbons. A hydrocarbon is a compound that contains the elements carbon and hydrogen only. There are no atoms of the other common elements that you often see in organic chemistry, such as oxygen or nitrogen, present in the molecule. Hydrocarbons are often referred to as fossil fuels. Let's first look at the alkanes. The alkanes are the simplest of all organic compounds, not just because they are hydrocarbons, but also because these molecules only contain single bonds. We would describe the alkanes as being saturated hydrocarbons, since every carbon already has 4 single bonds around it. In other words, the compound already contains the maximum number of hydrogen atoms possible, and no more can be added. Since every carbon atom has 4 covalent bonds around it, then of course every carbon atom in the molecule you see has a tetrahedral arrangement with an angle of 109.5 degrees. The only difference between members of the alkanes is the number of carbon atoms that they have strung together. To count these carbon atoms, chemists have developed a system of prefixes for naming compounds based on the number of carbon atoms in a given molecule. We can summarize these best in a table. Note that all alkanes end in the suffix -ane. When you see the name of a compound that ends in this, you know straight away that you are dealing with an alkane. You can see how we have a system of prefixes to represent the number of carbon atoms in a molecule. A molecule with 1 carbon atom has the prefix meth, giving us methane or methane. A molecule with 2 carbon atoms has the prefix eth, giving us ethane. A molecule with 3 carbon atoms has the prefix prop, giving us propane. A molecule with 4 carbon atoms gives us butane. A molecule with 5 carbon atoms gives us pentane. 6 carbon atoms gives us hexane. 7 carbon atoms gives us heptane. And 8 carbon atoms gives us octane. This is as far as you are required to go, but it's very important that you are familiar with these prefixes, as you will be using them all the time. This system is used right across organic chemistry for all the different families of compounds you will meet. So you can see with this combination of prefixes with the suffix -ane, we can easily and quickly name any alkane. Note that the last column in the table tells us the molecular formula of the alkane. This is useful, of course, but it's difficult to tell the structure of the molecule from a molecular formula. In organic chemistry, then, we often use other formulas that are better representations of the structure of the compounds, how the atoms are arranged relative to each other. These formulas are known as structural formulas. Here in this table, you will see the first 8 members of the alkanes, but now instead of the molecular formulas, we will have the structural formulas. You can see clearly that every carbon atom has 4 single bonds around it, and that the carbon backbone is extending by a single carbon atom with each successive member. Note that the structural formula is a flat drawing and it does not show you the shape of the actual molecule that you can see moving here. But these structural formulas give you a much clearer idea of the structure than you get from a molecular formula. They are much more representative of the actual molecule you can see. After some practice, you will be able to picture the shapes of molecules easily from a structural formula. It's very important to practice drawing these structures and testing yourself. Repeatedly drawing structures is the best way to learn organic chemistry. Let's now return to our previous table with the molecular formulas and examine in more detail what it means for organic compounds to be in the same family of compounds. In organic chemistry, we tend to refer to these families of compounds as a homologous series. A homologous series has several key characteristics. Each member differs from members on either side of it by a CH2 unit. You can see this if you look at successive molecular formulas. Each time we are effectively adding CH2 and extending the chain by 1 carbon. All members of a homologous series can be made in the same way. This usually means that they can be prepared by the same experimental setup, but from a different starting molecule, depending on which member you are making. We will see more about this later on in the relevant mandatory experiments. All of the members of a homologous series have similar chemical properties. This is not surprising for the alkanes, since they are just a chain of carbon and hydrogen atoms, the only difference between them being the length of the chain. As we shall see later with other homologous series though, often they have a key group in the molecule known as a functional group that gives the molecule its chemical properties. Since each member has these key functional groups, extending the chain by CH2 has no great effect on this, so they will all have similar chemical properties. The alkanes don't have a functional group as such, beyond the fact that they are saturated hydrocarbons. All members of the same homologous series can be described by the same general formula. This is a formula that relates the number of elements in a molecule to the number of carbon atoms in the molecule. You do not need to remember these for homologous series, and they are easy to work out from structural formulas at any rate. The general formula for alkanes is CnH2n+2. So for pentane, for example, which has 5 carbon atoms, there will be 2 times 5 plus 2, which gives 12 hydrogen atoms, as you can see from its molecular formula. Finally, members of the same homologous series show what we call a gradation in physical properties. This means that certain physical properties, such as boiling point, increase in a regular incremental way, such that the boiling point increases by a similar step with each member of the series. In the graph shown, you can see the boiling points of the alkanes. You can see that methane has the lowest boiling point at minus 164 degrees Celsius, but as you move up through the members, their boiling points gradually increase. This means we will gradually see a change in their state at room temperature. The first 4 members of the alkanes are gases at room temperature, whereas the next 4 members are liquids at room temperature. After you have 16 carbons and up, the alkanes are what we would call waxy solids, which simply means that they are soft. Candle wax, for example, has 25 carbon atoms. Understanding trends in boiling points and being able to compare boiling points of different homologous series is very important for the Leaving Cert. Why is the boiling point increasing as we move up through the alkanes? Well, the only thing that is changing is the molecular mass, so it must be caused by this. In alkanes, all of the bonds are pure covalent, and the molecules are extremely nonpolar. This means in turn that the only intermolecular forces between these molecules will be van der Waals forces, and since we know that van der Waals forces depend on the molecular mass, then as this increases, so too will the melting and the boiling points, as we've seen. When we compare the molecular masses and boiling points of methane and octane, for example, we can see this very clearly. Methane has a very low molecular mass of 16, whilst octane has a molecular mass of 114. This means that there will be only weak van der Waals forces between methane molecules, since there are very few electrons in these molecules to generate temporary dipoles. Hence, methane has the very low boiling point of negative 164 degrees Celsius. Octane, on the other hand, is a much bigger molecule with a molecular mass of 114. This will mean that there will be much stronger van der Waals forces between these molecules, as there are a much greater number of electrons in these molecules to generate temporary dipoles. Hence, octane will have a much higher boiling point of 174 degrees Celsius. So despite the fact that van der Waals forces are quite weak intermolecular forces, you can see here how they can still make a big difference to the melting and boiling points of nonpolar organic substances. We can see this trend throughout all homologous series. As we add extra CH2 units, the molecular mass increases, and so too does the melting and boiling points. All that is different between different homologous series is how low or high the starting boiling point is, depending on what functional groups are in that homologous series, as you can see from the graph. Next, we will look at the system we use to name organic compounds. We have already seen from the alkanes that naming the alkane depends on the number of carbons in the molecule. However, it's not quite that simple. This method of naming the alkane applies only to the longest chain of carbons in the molecule, and it doesn't take into account the possibility of side chains. You can see from the table that the number of carbons in the longest chain, the first column, will give us the name of the alkane if there are no side chains, but we will have to add to this if there are any. Side chains can be anything, but the most common type of side chain for alkanes are alkyl groups, which are hydrocarbon side chains as shown. You can see that we named them in the same way as we did the longest chain, using meth, eth, prop, bute, etc. But now we add the suffix "-yl" to denote that it's a side chain rather than a part of the longest chain. In this first example, you can see straight away that we have a side chain. The first thing that we must do is identify the longest carbon chain. Here you can see that the longest carbon chain is 5 carbons long. This means that our molecule would be simply pentane if there were no side chains. However, we do have a side chain, and whenever we have a side chain, we must number the carbons in our longest chain, such that the side chains are on the lowest possible numbered carbons. In this case, this means that we will number our carbons from the bottom, as shown, and our side chain will be on the second carbon. We can now look at what the side chain is, and we see that it is a methyl group. So we will name the compound like this: 2-methyl to show that the methyl group is on the second carbon, and pentane to show that it is attached to a straight chain that is 5 carbons long. In this molecule, you can see again that we have a longest chain of 5 carbon atoms. We are again dealing with pentane then. In this situation, however, we have 3 side chains, all of which are methyl groups. We must therefore number our longest carbon chain such that the side chains are on the lowest possible carbons. This will mean numbering from the bottom so that 2 of the side chains are on the second carbon and only 1 on the fourth. Here is how we name this molecule. Since we have the same side chain 3 times, we can keep our numbers together to make it easier, so it will be 2,2,4, and then we must say trimethyl since we have 3 methyl groups, and then pentane for the longest carbon chain. In this molecule, you can see again that we have a longest chain of 5 carbons. We are again dealing with pentane then. In this situation, however, we have only 2 side chains, but they are different. One is a methyl group, and the other is an ethyl group. Again, we must make sure that we number our carbon atoms such that the side chains are on the lowest numbered carbons. This means starting from the bottom, so that the methyl group is on the second carbon, as the ethyl group will be on the third carbon no matter which end we start from. Since we have different side chains, we would name the molecule like this: 3-ethyl, 2-methyl pentane. Ethyl precedes methyl alphabetically. These give us the basic rules for naming organic compounds. There are other rules, of course, for other homologous series, but we will deal with those when we get to them. We mentioned earlier that alkanes can also form what are called cyclic or ring compounds. These are when the carbon atoms are connected in a circle or a ring. The most important example you should know is cyclohexane, C6H12. As you can see from the structure of cyclohexane, each carbon atom is joined to 2 other carbon atoms and to 2 hydrogen atoms. This means, of course, that each carbon atom has 4 single covalent bonds. It's a saturated hydrocarbon then, to which no more hydrogens can be added, and so it's an alkane. Because there are 6 carbon atoms in the ring, it is known as cyclohexane. Again, the best way to learn structures like this is to practice drawing them. Be careful not to confuse this structure with benzene. Benzene has the formula C6H6 and a very different type of bonding, which we will see shortly. Now that we understand how to name these molecules with side chains, we are ready to look at structural isomers. Here you can see the structural formula of butane with the molecular formula C4H10. You can see that it's unbranched. What if we take another molecule of butane, but if we rearrange some of its atoms by swapping a CH3 unit from the end of the chain with a hydrogen atom in the middle of the chain? This molecule still has the same molecular formula C4H10, as we have not changed the number of atoms it has, we've just rearranged them. But you can see that this molecule has a completely different arrangement, as shown by its very different structural formula. This molecule is methyl propane. Notice that we don't say 2-methyl propane, as the second carbon is the only possible location for a side chain. If it was on the first or third carbon, then we would just have butane again. In other words, we don't need to specify to which carbon atom the side chain is attached, unless there is more than one possibility. This gives us the very important and regularly asked definition for structural isomers. They are molecules that have the same molecular formula, but different structural formulas. It's easy to find out if a molecule has more than one structural formula by following this approach of taking carbon atoms off the end of the molecule and adding them as side chains to see if you get a different structure. Let's look at another alkane whose isomers you are required to know. Here we have the alkane pentane with 5 carbons arranged in a single chain with no side chains, and the molecular formula C5H12. There are actually 3 isomers of C5H12. The straight chain isomer you see here is the first isomer, but there is also the isomer you get when you take one of the carbon atoms at the end of the chain off and add it as a side chain. This isomer of C5H12 is 2-methylbutane. If we now go further and remove another CH3 unit from the end of this molecule and swap it with a hydrogen atom on the second carbon, we get another isomer of C5H12. This isomer is 2,2-dimethylpropane. No further isomers are possible from here, so there are only 3 isomers of C5H12. Make sure you remember them. The next hydrocarbon homologous series we will look at are the alkenes. Alkenes are named from the corresponding alkane by changing ane to ene. Alkenes have at least one double bond between 2 carbons in their structure, and as such they are unsaturated molecules. An unsaturated compound is one that contains at least one double or triple bond between atoms in the molecule. This effectively means that it's possible to add more hydrogen atoms to the molecule. Since we require a carbon-carbon double bond in alkenes, the first possible member of the alkenes is ethene, since we require a minimum of 2 carbon atoms to have this double bond. There is no such compound as methene then, and the first member of the alkenes is ethene. Here, if we look at the structure of ethene, we can see clearly what it means to be unsaturated. Because of the double bond between the carbon atoms, each carbon atom only has 2 remaining bonds to bond with hydrogen, and so the formula is C2H4. From this you can straight away see that the general formula for alkenes is CnH2n. If we now convert the double bond to a single bond, we can see that each of the carbon atoms' valency is not satisfied. They must have 4 bonds around them. In this way we can add another hydrogen atom to each carbon to get the corresponding saturated alkane, ethane, C2H6. This is the difference between a saturated and an unsaturated molecule. Naming alkenes follows much the same pattern as we saw earlier for naming alkanes. You just need to identify the longest carbon chain, side chains, etc., and go from there. You are required to know the first 3 members of the alkenes. Ethene with 2 carbon atoms we've already seen. Next comes propene with 3 carbon atoms. Notice with propene that it does not matter where you put the double bond. If you put the double bond on the other side, it's still the same molecule, just viewed from the other side. Next we have butene. But now we have to pay attention to the location of the double bond, as there are 2 possible locations. Here you see but1ene, which indicates that the double bond is on the first carbon atom. However, one of the structural isomers of but1ene is but2ene, where we move the double bond to the second carbon. Again, these 2 molecules have the same molecular formulas, but different structural formulas. Butene has a third isomer, which we can form by moving a carbon from the end of the chain to a side chain position as we did before. This gives us methylpropene. As with the alkanes, successive members of the alkenes show gradations in physical properties. The boiling points of the alkenes increase steadily as the number of carbons increase, and the strength of the van der Waals forces between them correspondingly increase too. Lastly, you must pay careful attention to the geometry of carbon atoms in alkenes. Whilst all the carbon atoms in alkanes were tetrahedral, since they all had 4 bonds around them, in alkenes carbon atoms may be either planar or tetrahedral. Let's look at but1ene as an example. Here you can see that the 2 carbon atoms on the left in orange each have 3 bonds around them. This means that both these carbons will be planar carbons with a bond angle of 120 degrees. If you turn the molecule, you will be able to align these carbons with the atoms attached to them in a single plane. The two carbons on the right in blue, however, have 4 bonds around them, and so these are tetrahedral carbons with a bond angle of 109.5 degrees. If we look at one of the isomers of but-1-ene, methylpropene, we can again quickly see if a carbon atom is planar or tetrahedral based on the number of bonds it has around it. The two carbons on the left, as you can see, are planar as they are attached to the double bond, and so have 3 bonds around them, whilst the other 2 are tetrahedral. Identifying how many carbon atoms in a structure are planar or tetrahedral is a very common question on the Leaving Cert, so it's very important that you can first draw all of these structures and then identify the geometry of the carbon atoms based on the number of bonds they have around them. The last homologous series of the hydrocarbons that we must look at are the alkynes. Alkynes are named from the corresponding alkanes by changing ane to ine. Alkynes are characterized as having a triple bond. As with the alkenes then, this means that the first member of the alkynes is ethyne, with a formula of C2H2. This is actually the only member of the alkynes that you're required to know for the Leaving Cert, and we will speak more about it in Mandatory Experiment 13.2. All of the types of compounds we have seen so far are referred to as aliphatic compounds. Aliphatic compounds can be arranged in open chains of carbon atoms that may be either branched or unbranched. We've also seen closed chain compounds where the carbon atoms are arranged in rings. There are also other types of organic compounds that are referred to as aromatic compounds because the first examples of these compounds discovered had sweet smells. These type of compounds contain what is called a benzene ring, a very special structure in organic chemistry. When benzene was first discovered, it was quickly found to have a formula of C6H6. The structure shown was therefore proposed by the German chemist Kekulé, where a ring of 6 carbons had alternating single and double bonds. This was the only bonding that satisfied the molecular formula for benzene under the usual rules of bonding. Chemists quickly made some observations, however, that were inconsistent with this structure. They found that benzene did not undergo addition reactions, which are typical for compounds that contain a double bond and are unsaturated. They also found that the distance between the carbon atoms was not as you would expect. Double bonds are shorter than single bonds, and in benzene it was found that actually all of the bonds are of equal length. Lastly, there were no isomers observed for benzene, which would have been expected if it had this structure. Chemists therefore had to investigate other possible structures, and what they found was very unusual. Let's take this structure here, which has single bonds between all the carbon atoms. This satisfies the observation that all the bonds are of equal length at least. Note that each carbon has 3 sigma bonds in the structure shown. It has 2 sigma bonds with the 2 carbon atoms on either side of it, and 1 sigma bond with its hydrogen atom. This means that there are 12 sigma bonds present in benzene altogether. But of course carbon has 4 electrons, so where is the 4th electron? Well, the 4th electron of each carbon atom is in a py orbital that is perpendicular to the plane of the ring. To help us visualize this, let's replace the carbon atoms with a hexagon, where each corner represents a carbon atom, and the line between the corners the single bonds. And let's remove the hydrogen atoms. You can remember that there is 1 hydrogen attached to each carbon or the corner of the hexagon. If we rotate the molecule, we can see the py orbital of each carbon atom that holds the 4th electron. Chemists propose that rather than these 6 electrons occupying 3 double bonds, that they are delocalized. Delocalized electrons are simply electrons that are shared between more than 2 atoms. In other words, the 6 electrons from each carbon atom in the py orbitals are shared across all 6 carbon atoms. This cloud of delocalized electrons, which exists above and below the plane of the benzene ring, is represented by a circle inside the hexagon. The key features of this structure then is that there are 12 sigma bonds present, 6 between the carbon atoms and 6 between the carbon and hydrogen atoms. The delocalized pi electrons form a cloud that are shared equally across the carbon atoms and explain why we have equal bond lengths intermediate between single and double carbon-carbon bonds, since the delocalized electrons pull the carbon atoms closer than they would be if there was just a single bond between them, but not quite as strong as a double bond. Benzene is very stable and does not undergo addition reactions because it does not have double bonds and is not unsaturated. It therefore doesn't decolorize bromine water or acidified potassium permanganate. Benzene is a planar molecule, as you can see, and it is a known carcinogen. There are 3 aromatic compounds that you are expected to know for the Leaving Cert, and they are shown in the table. Methylbenzene is also known as toluene and is used in the making of the explosive TNT. Ethyl benzene is used primarily to make polystyrene for packaging, but is also a good solvent. Benzene itself is also a good solvent and is a good precursor for making plastics and synthetic fibers. Notice from the rotating molecules that you can clearly see that all of the atoms in the benzene ring are in one plane. All 6 carbon atoms are planar, whereas all of the carbon atoms in the side chains are tetrahedral carbons, with 4 bonds around them. That's it for section 13.1. Have a go at the questions.